Hello and welcome to this lecture series on convolutional neural networks. In this lecture series, we shall delve into the topic of CNNs and explore the working of CNNs. Convolutional neural networks are widely used in image processing for computer vision applications. What we will try to establish in this lecture series is to develop a clear understanding of what a convolutional neural network is, what is the convolution process, and get a clear, in-depth understanding of the implementation of the convolutional neural networks. So the objectives of this lecture series is to develop a comprehensive understanding of convolutional neural networks and their working. So we shall explore the working of CNNs in detail. And then we also want to have a general understanding of the advantages of convolutional networks and the applications of CNNs. So we will be talking about how the convolutional networks differ from conventional neural networks, and what advantages do they provide, and what are the applications of CNNs. And then we also want to focus on developing a clear understanding of the convolution process itself, because at the heart of the convolutional neural network is the convolutional process, where the input image is convolved with some filter, and that produces an output image. So at the heart of the CNN lies the convolution operation. So we need to have a clear understanding of what the convolution process is. So we will investigate and develop a clear understanding of the various steps involved in convolutional neural networks. And in particular, as we go along this series of lectures, we will focus on the convolution process itself in quite a bit of detail. And then once we have done these, we should have a fair bit of appreciation for how convolutional neural networks differ from conventional neural networks. When we talk about conventional neural networks, we mean fully connected neural networks. Again, what is meant by that and how CNNs differ from fully connected neural networks, we will discuss about that in due course as we go along in this series of lecture videos. So, what does a convolutional neural network look like, and what does it do to a given input signal or an input image? And let us start without going too much into the details of the mathematical calculations, but rather we'll focus our attention at this point of time as to the dimensions, how the dimensions of the input image are affected as a result of each convolution operation. So we will have an appreciation for what the convolution operation does to an input image, and then later on we will extend this idea to actually understand how the convolution itself is performed. So typically in a convolutional neural network, we have multiple levels of convolutional layers. So as you see in this illustration on this slide, we have a convolutional layer number 1, and there is a second convolutional layer which we call convolutional layer 2, and then there is a third layer, and so on and so forth. And as the number of layer increases, that means the depth of the convolutional neural network is increasing. So in deep neural networks or deep CNNs, excuse me, the number of convolutional layers will be quite large, and that is when we have deep convolutional neural networks. So what happens is an input image is typically passed through multiple layers of convolutional processes, and that generates an output, and that final output is used as sort of features which is used by some prediction or classification mechanism to predict something about that input image, or to classify that input image into one class or another. So the entire process of the CNN is to pass the input image through multiple stages of convolutions to generate what we call as a set of features at the output of it, and those features would be used for some form of prediction or classification. So in this particular illustration that is shown on the slide, the convolutional neural network has 3 layers, as we mentioned earlier. In fact, in this particular illustration, we have shown only the convolutional layers, but in practical implementations, there will be some other layers in addition to the convolutional layers, and those could perform other functions, okay, which we will delve into in due course as we go along in this lecture series. But for now, let us just focus on the convolutional layers and develop an understanding of what the convolution process does to the input image as the input image passes through each convolution layer. So let us now focus specifically on the dimensions of the input and output image at each convolutional layer, and we will not worry too much at this stage about the details of the filter and the convolution operation itself. Okay, we'll talk about that later. Okay, so what do we observe happens to the dimensions of the input as it passes through the convolution layer? So we have the first convolution layer, which has an input image. It has a certain filter, so the input image is convolved with some filter, and that produces an output image. And that concludes the first layer of the convolution process. That is the processing at the first convolutional layer. The output of the first convolutional layer becomes the input to the next convolutional layer, which is the second layer, and there the output of the first layer is convolved with the filter in the second layer, and that results in an output for the second layer, which in turn becomes the input to the third layer, and so on and so forth. But what is the observation that we notice here as the input image moves deeper into the convolutional neural network? If you look at the input image here, it has a dimension of 39 by 39. That is, the width of the image is 39 pixels and the height of the image is 39 pixels, and it has a depth of 3 channels. So again, when we talk about depth, we talk about the number of channels. For a color image, the number of channels is 3: the red channel, the green channel, and the blue channel, the RGB channels, right? So we have a color image of dimensions 39 by 39 pixels and 3 channels, and when this is passed through the convolutional network, we notice that the output that is obtained here is 37 by 37 by 10. Again, how we get these numbers, we'll discuss about that in a subsequent video. But for now, let us just see that the dimension of the pixels, which was 39 by 39, is reduced to 37 by 37 at the first convolutional layer, and in the second convolutional layer, the pixel size, or the image height and width, which was 37 by 37, is reduced to 17 by 17, and later on it is eventually reduced to 7 by 7, and so on. So in general, what we notice is that the convolution process reduces the dimensions of the input image. So the image becomes smaller and smaller in terms of its width and height. However, what we notice in terms of the number of channels is that the number of channels keeps on is increasing as we go from one convolution layer to the next convolution layer. So initially the input image had 3 channels, and at the output of the first convolutional layer, the number of channels in that output is 10, and the number of channels at the output of the second convolution layer is 20, and the number of channels at the output of the third convolution layer is 40 here. So what we notice is that the dimensions in terms of the width and height are becoming smaller and smaller, and the dimension in terms of the number of channels is increasing as we go deeper into the convolutional network from one convolutional layer to the next convolutional layer. And what happens after the final convolutional layer is whatever data is available in the output of the final convolutional layer, that is flattened by what is called as a flattening layer, which basically takes out all the pixel values and arranges them as a single vector. So this is a 7 by 7 image with a depth of 40 channels, so there are 40 layers of 7 by 7, so a total of 1960 pixels, and these are all arranged as a single vector by what is called as a flattening layer, and this vector becomes the feature vector, which is used by the classifier, or it could be a predictor to predict something about the image or to classify the image or some object within that image. So overall what we notice is that the dimensions of the image in terms of the width and height decreases as it goes through through the convolutional layers, and the number of channels increases as it goes through the convolutional layers. So which is what is highlighted here. So size of the image, width and height decreases, however the number of channels increases. So now let us see an illustration of the how the convolution happens. Of course, we're not going to go through the working of the convolution operation itself, but we just want to see how we get the change in those dimensions between the input and output. So we have an input here for simplicity, rather than taking an input with a large number of pixels like 39 in the previous slide. So we have reduced it down to a 6 by 6 input image with 3 channels. So the 3 channels are the RGB channels, the red channel, the green channel, and the blue channel. So it's a 6 by 6 input, so the number of pixels is 6 in the rows and columns. So we have 6 rows and 6 columns, and the size of the filter that is used here is a 3 by 3 filter. And what we notice here is that when we are performing convolution between an input image and a filter, we have to make sure that the number of channels in the filter is the same as the number of channels in the input image. And since we have 3 channels in the input image, we have to choose a filter with 3 channels. So the dimensions of the filter could be anything, but the number of channels must match the number of channels in the input image. So that's the first observation that we see. And how do we compute the output? So the size of the filter, which is in this case 3 by 3, that determines the size of the window that will be used for the convolution. So because we have the filter size as 3 by 3, we use a window size of 3 by 3 in the input image. So we have a 3 by 3 window for the red channel, a 3 by 3 window for the green channel, and also a 3 by 3 window for the blue channel. So each of the channels has a window whose dimensions are the same as the dimension of the filter, and then we compute the first pixel value of the output by performing an element by element multiplication of the input pixels within each window with the corresponding channel of the filter. So for the red channel of the input image, we take the 9 pixels which are present within that window and multiply with the 9 values of the filter on the first channel of the filter. Similarly, the 9 pixels on the green channel are multiplied with the 9 filter values from the second channel of the filter, and similarly the third channel, or the 9 pixel values from the blue channel of the input image are multiplied with the 9 values of the filter from the third channel of the filter. So after performing these element by element multiplications, we have a set of 27 numbers, and these 27 numbers are all added together to get the first pixel value of the output. So this first pixel value of the output is basically an element by element multiplication of the window of the input image with the filter, and we do that for each of the channels, and we end up with 9 numbers for the first channel, 9 numbers for the second channel, and 9 numbers for the third channel, which are products between the filter and the pixels within the windows. And those 9 plus 9 plus 9, which is 27 values, are all added together to get the first pixel value of the output. And what we do next is we slide this window to the right by 1 pixel. So we have this sliding of the window by 1 pixel to the right. So we have moved 1 column to the right on each of the 3 channels, the R channel, the green channel, the red, green and blue channels. And this shift to the right, that is called as the stride of the window. So the window is striding by 1 pixel step in this particular case. Of course, as we will see later, the value of the stride can be more than 1 as well. We will see what effect that creates later on, but for now we will choose the stride value as 1. So the window has moved 1 pixel to the right, and as the window has moved 1 pixel to the right, we compute the second pixel value of the output, which is again element by element multiplication of the pixels within each of the window or with the corresponding channel of the filter. So the red channel pixels within the window, we have 9 such pixels within that window. Those 9 pixels are multiplied with the first channel of the filter, and similarly the 9 pixels of the green channel are multiplied with the 9 elements of the second channel of the filter, and the 9 pixels of the third channel, which is the blue channel, are multiplied with the 9 elements of the third channel of the filter. And these element by element products, which will result in 27 numbers, which will all be added together to get the second pixel value for the output image. And we will keep shifting this window step by step until we have strided to the rightmost edge of the input image. So we can move 1 step forward now. So that has brought us to the third pixel now, and that allows us to compute the third pixel in a similar way as we have discussed for the previous 2 pixels. And after computing the third pixel, we again stride forward by 1 more step. Again, the size of the stride we are using here is 1. So when we move forward 1 more step, we get the 4th pixel value. And notice now that the window in the input image, the 3x3 window that we have used, it has reached the end of the image. It has reached the last column of the input image for each of the 3 channels. So as the window moves from left to right, we see that we have got 4 windows. We're starting from the leftmost window to the rightmost window. We have got 4 windows in this particular case, and that is why we have 4 columns of pixels in the output image for this particular illustration. Now that we have reached the end of the columns of the image, that means the window cannot stride forward any further. So we cannot move this window any further to the right. So that means the last pixel in terms of the columns will be the 4th pixel. So the output image in this case will have 4 columns. That's the column number 1, column number 2, column number 3, and column number 4. So we have computed all the 4 columns of pixels for row 1 of the image. So once we have obtained the first row, we now need to shift the window downward by 1 pixel and bring it back to the leftmost edge of the image. So that will take us to the second row, okay, to a window which starts from the second row of the image, and the window size is again the same as the filter size, which is 3x3. So that's a 3x3 window for the red channels. Similarly, there is 3 by 3 window for the green and blue channels as well. And all of these windows will now start from the leftmost column of the second row of the input image. And similarly, multiplying element by element for each of these channels and adding those numbers will result in the pixel, the first pixel of the second row for the output image. And if we keep shifting this window forward, we will get the 4 columns of pixels for the second row, and then we move down one step and so on and so forth until we get to the final corner of the input image, and that will give us an output image which is going to be 4 by 4, because as we go from left to right we get 4 windows of pixels in the input image. So correspondingly we get 4 columns of pixels in the output. And similarly, as we go from top to bottom, as we stride this window from top to bottom, we will get 4 windows as well, and that will result in 4 rows of pixels for the output image, and therefore the output image is going to be a 4 by 4 image. So we started off with a 6 by 6 input image, and the output is going to be a 4 by 4 image. Of course, the number of channels in the input is 3, but in the number of channels in the output that we are getting in this particular illustration is only 1. And the reason is because we have used only a single filter, which is of some size 3 by 3. So the number of channels in the output, that depends on the number of filters that we use in the convolution process. And generally in a CNN implementation, the number of filters used is such that the number of channels in the output is usually more than the number of channels in the output, okay, in the input rather. And however, for this illustration I have taken only a single filter with 3 channels, and the output is a 4 by 4 image with a single channel. Okay, now we will extend this idea to see what happens when the number of filters is increased. So clearly we see that the number of channels in the output is equal to the number of filters that are used for the convolution process. And since we have used only a single filter here, we get a single channel output whose dimension in this case is 4 by 4, because as we stride from left to right with a window size of 3 by 3, and as we stride from top to bottom, we get 4 windows at most. So the output dimension is 4 by 4. So now let us look at an example where we use 2 filters. So the first filter will produce a 4 by 4 output, and that constitutes channel 1 of the output. So we have channel 1 of the output given by this representation. So the input image is convolved with one particular filter whose dimensions are 3 by 3, and it has 3 channels. Of course, we should always ensure that the number of channels in the filter matches the number of channels in the input image, and because the input is having 3 channels, the filter should also have 3 channels. So filter is also having 3 channels. However, the size of the filter need not be the same as the size of the input image. So the input image here is 6 by 6 with 3 channels. The filter size is 3 by 3, also with 3 channels. And the first filter produces an output which is 4 by 4, and that the output corresponding, the 4 by 4 output corresponding to the first filter constitutes the first channel of the output. Similarly, when we perform a convolution between the input image with a second filter of the same size and the same number of channels as the input, that produces another output which is having a dimension of 4 by 4 as before, and this output constitutes the second channel of the output. And in this way we can have a third channel and a fourth channel and a fifth channel and so on and so forth, and a third filter and a fourth filter and so on. correction there. We can have multiple filters rather than channels. Okay, just as we have filter 1 producing channel 1 of the output, filter 2 producing channel 2 of the output, we can have filter 3, filter 4, filter 5, and so on, and each of the filters outputs will constitute a specific channel of the output. So the output of filter 1 is channel 1 of the output of filter 2 is channel 2 of the output of filter 3 would be channel 3 of the output of filter 4 would be channel 4 of the output, and so on and so forth. So we get an output whose dimension is 4 by 4 into the number of filters. So the number of filters in this case is 2, filter 1 and filter 2. So therefore we have an output which is 4 by 4 by 2. That means the output is 2 channels. And however, we have seen in our earlier slide that in general, the convolutional neural network, as the image passes through it, the dimensions become smaller, but the depth or the number of channels becomes larger. So the number of filters is typically going to be more than 3. So the depth or the number of channels in the output is going to be more than 3. However, for the sake of illustration, I've shown only 2 filters and therefore only 2 channels in the output. Okay, but in practice, generally, the number of channels in the output is going to be usually more than the number of channels in the input. That means the number of filters that we will use will usually be more than the number of channels in the input image. So now, taking all this, let us try to give some notation to these dimensions and try to get a relationship between the dimensions of the input image and the output image. Overall, we know that as we perform convolution of an input image with a filter, the general observation is that the dimensions of the output in terms of the width and height will be smaller than the dimensions of the input. However, the number of channels in the output would increase as we perform the convolution. So let us give some notation to each of these parameters. So let's say the dimensions of the input, which we have used as 6 by 6. Let's call the dimension as n by n. So the width and height are denoted as n, and the number of channels in the input, which is 3 in this illustration, we'll denote that as n sub c. So that's the number of channels in the output. The dimensions of the filter is denoted as f by f, which is 3 by 3. We are using each filter of dimensions 3 by 3 pixels. So the width is 3 and the height is 3. So that is denoted by the letter f. So that's f is equal to 3. So we'll have 3 by 3. And the number of channels of the filter is also NC, because the number of channels in the filter must match the number of channels in the input image. So the number of channels in the filter is also NC. And then we have another parameter called padding. However, we'll talk about padding later, but for now we'll just take the value of the padding parameter, which we denote as P, to be 0, and the stride is the number of pixels by which the window moves from left to right or from top to bottom. So that stride value, in the illustration that we have seen, we have used the stride value as 1. So we denote the stride by the parameter s, and the stride value we have used is 1. Now, based on these notations, what is the relationship between the input image and the output image? And the final parameter of interest for us is the number of filters itself, which we denote by n underscore f, which is the number of filters. And for our illustration, we have used the number of filters as 2. So now with this information, let us try to get some understanding or relationship between the dimensions of the output image and the input image. So the dimensions of the output image is going to be n plus 2p minus f divided by s plus 1 times n plus 2p minus f divided by s plus 1 times the number of filters nf. So this is the general relationship uh, between the input dimensions and the output dimensions. So let's put in the values that we have for our illustration here into the dimensions of the output image, and see that it matches the 4x4 output that we get for each channel, and the number of channels is indeed 2 because we have the number of filters NF as 2. So the value of n in our example is 6, so n by n is the input image, so n is 6 by 6, so we'll substitute 6 for n. The padding value we are using 0. Okay, we'll worry about the padding at a later point. So the padding p is 0, so it's 6 plus 2 times 0, so that's 6, minus f. F is the dimension of the filter, which is 3 by 3, so it's 3. F value is 3, so it is 6 plus 0 minus 3, so that is basically 6 minus 3, which is 3, divided by the stride value s. So we have used the stride value s equal to 1, so 3 by 6 minus 3 is 3, divided by 1 is still 3, and that 3 is added to 1, so 3 plus 1 is 4. So this parameter on the left here, the first number here for the dimensions, becomes 4, and similarly the second number also becomes 4. That is 6 plus 0 minus 3 divided by 1, which is 3, plus 1 is 4. That's why we get an output image whose dimension is 4 by 4 times the number of filters. So we have 2 filters here, so we get 2 channels for the output. If we had only 1 filter here, we will get only 1 channel in the output, which will be simply 4 by 4. So in this case, in our example here, we have the number of filters as 2, so we have, that's the first filter, which is shaded in pink, and the second filter, which is shaded in yellow. So these 2 filters produce each of the 2 channels of the output. So the output dimension in this case is 4 by 4 by 2. So the width and height of the output image is 4 by 4, and there are 2 such channels for the output. So there are 2 channels, each of size 4 by 4, and if we had 10 filters, then the output would be 4 by 4 by 10. Generally, the number of filters is more than the number of input channels, and that is why we will see that in CNN, as we perform convolution through the layer, one layer after the other, the depth of the output image, or the number of channels in the output, keeps on increasing as we go through the convolution processes. Now let us have a quick overview of what this padding is. I have introduced a new term called padding here. Let me give you a quick overview of what this padding is and why it is needed to be done. However, we'll talk about the details of padding in subsequent videos. So what is padding is basically adding an additional layer of pixels, or one or more additional layers of pixels around the original image. So we have this original image given by these numbers in black, which are the pixel values, and we are adding one layer of padding around the entire image. Okay, in this particular example, again, the padded pixel values are chosen to be zeros. However, there are other ways of choosing the padding values as well. So by using the padding, we are basically changing the input image size to a different value. So we have an original input image, which is 6 by 6 image, so it has 6 rows and 6 columns, to which we are adding 1 pixel of padding all around it. And after adding 1 pixel of padding all around it, the dimensions of the padded image becomes 8 by 8. So if you look at this, it's 1 2 3 4 5 6 7 8. So there are 8 columns, and similarly there are 8 rows. So after 1 layer of padding, or 1 pixel padding around the entire image, we have converted a 6 by 6 input image into a 8 by 8 input image. And then we will perform convolution with some filter. Again, I have given some specific value for the filter here, a specific type of filter is used. Again, what is that and how is the computation taking place? We will talk about that in detail in subsequent videos. However, what we notice is that when you perform this convolution between this padded input image with the 3x3 filter, so the dimensions now is the value of n becomes 8. So it's the input becomes the input image is still n 6x6, but the padding value is 1. P is equal to 1. So the output dimension is now going to be n plus 2p minus f. N is 6 plus 2 times 1 is 2, so that's 6 plus 2 is 8. And 8 minus f, f is 3. The size of the filter is 3x3. So 8 minus f is which is 8 minus 3 is 5, plus 1 we will get a 6 here. So the dimension for the output image is now 6 by 6. So we started off with a 6 by 6 original image. We added a padding of 1 pixel around it, and after convolution we get an output which is again 6 by 6. So padding is generally used in situations where we require that the size of the output image in terms of its width and height remains the same as the size of the input image. So we have an input image of 6 by 6. Generally, as a result of convolution, the output will be smaller than the input dimension in terms of the width and height. But by padding, we are able to get back an output image whose dimension is the same as the input image, which is 6 by 6 in this particular case. In general, what we can do is, given an input dimension for the image, we can determine what should be the number of pixels that should be padded in order to maintain the output dimensions of the image to be the same as the input dimensions. So we know that the output dimensions are given by this particular expression at the bottom here, and we want that output dimension to be the same as the input dimension of the image, which is n. So equating these two and simplifying, we get the number of padding pixels that are required as f minus 1 upon 2. So f is the size of the filter, which is in this particular case is 3. So it's 3 minus 1 is 2, divided by 2 is 1. So the number of padding pixels required in this case is p equal to 1, and that is why we have used 1 pixel padding all around the image. And after adding this 1 pixel padding, we notice that the size of the output image is the same as the size of the input image. So we have seen what convolution does to an input image in general, and we are focused in this video specifically on how the dimensions get changed as we perform convolution. And the takeaway that we have is that the dimensions in terms of the width and height of the image become smaller and smaller as we perform the convolutions. However, the dimension in terms of the depth of the image, that is the number of channels, that increases as we go from one convolution layer to the next convolutional layer. And then we also introduced the concept of padding, in situations where we need to have the dimension of the output to be the same as the dimension of the input. So far, I hope that this video has given a high-level overview of CNNs and the convolution process, and also given us a clear understanding of how the dimensions of the image are affected by the convolution process. Okay, we will talk about more details of the convolution operation itself and its various implementation variations in terms of padding, the amount of padding, and also variations in the size of the stride. Rather than using the stride value s equal to 1, we can use s equal to 2 or so on. So we will see what these variations produce and how it affects the dimensions of the output data or the output image, and how the relationship between the input and output image is affected when we change these parameters. So these parameters like the stride, the padding, the dimensions of the input image, the number of filters, these are called as the hyperparameters of the convolutional neural network, which are basically the design parameters and by altering these parameters we can change the output that we get through the convolutional network. Okay, so hopefully this video has given a high level overview of convolutional neural networks and how the dimensions are affected as a result of the convolution process. And we will discuss about the convolution process in more detail by working out the convolution between an input image and a specific filter. Like in this case, we have an input image with specific pixel values and a filter with specific values for each of its parameters, and we'll perform convolution between this input image and the filter and compute each and every pixel value of the output, and we'll see how the computation is done for the convolution. And of course we will do that for different values of the parameters for padding, as well as the stride, as well as the dimensions of the filter and the number of filters and so on. Okay, stay tuned, and we will cover CNNs in more detail, and hopefully at the end of this series of videos we will have a clear understanding and an in-depth understanding of convolutional neural networks and their operation as well as their implementations.